Hi, this is a continuation of the homework problems for test 2 in linear algebra, math 231. Okay, so now we are up to 4.7. Last video we finished 4.6. We did 4.6, so 4.7, the problems were numbers 15 and 17. And so let's look at number 15. Okay, so for number 15, page 247, the problem is find a basis for the subspace of R4 spanned by the given vectors. So the given vectors, these are the given vectors. Okay? These four are the given vectors, and we want to find the subspace of R4 spanned by those vectors. Okay, so if we make a matrix whose rows are these vectors, okay, then we can just get this matrix to reduced row echelon form, and the rows with leading ones, those vectors will span the same subspace of R4 as the original 4 vectors. So we're going to get this matrix to reduce row echelon form. These are the rows. This is the first row of the matrix. This is the second row. This is the third row. And this is the fourth row. Okay, so I'm just going to find the row space of this matrix by getting it to row echelon form, and then I actually only need row echelon form. Row echelon form, and then looking at the rows with leading ones. So I'm going to take 2 times the first row and add it to the third. And so here's the first row. I'm going to take 2 times that row and add it to the third row. And so I'm going to get 0, 2, 2, 2. And then I'm going to take, I'm going to get rid of this 3. I'm going to take, actually, so I'm going to keep that the same for a minute. I'm going to multiply this by 1/2. And I'm going to move it to the set. I'm going to switch these 2 rows. I'm going to make this the second row. And so I'm going to get 0, 1, 1, 1. And I'm going to move this to the third row by switching the second and third row here. I'm going to get that. And then this row is going to stay the same for a minute. And then I'm just going to take 3 times this row and add it to that row. And so we get 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1. And then the last row, I'm going to get 3 times this row added to this one. I'm going to get 0, 0, 3, 6. And then I'm going to take -3 times this row and add to that row. And I'm going to get -3 times this row added to that one. I'm going to get 0 here, and I'm going to get a 3 here. And then I'm going to multiply the fourth row by 1/3. And then, eureka, we have our matrix in row echelon form. Multiply that by 1/3. And now we have our matrix in row echelon form. And every row of this matrix is has a leading 1. Okay, so so it turns out that these 4, if I wanted to know the span of the rows of this matrix, I would have to take all 4 of these matrices. So all 4 of these rows are needed to span the row space of R, that matrix in row echelon form. But then I could take the corresponding rows of my original matrix, and I would need the same 4, all 4 rows, to span the row space of R. And so the conclusion is actually that, so find a basis for the subspace spanned by the given base. If I called this V1 and I called this V2, I called that V3 and that V4, I could say that V1, V2, V3, V4 is such a basis. That's the answer. So actually the answer is that just use all the vectors in the given problem. These are linearly independent. You need all 4 of these vectors to span the subspace of R4. The span of these 4 vectors is actually, you need all 4 vectors for the span. So the conclusion is taking the set containing all 4 vectors is such a basis. Okay? Okay? Okay, so again, the row space of R, a basis for the row space of R is all 4 rows of R, because there's a leading one in every row. Correspondingly, a basis for the row space of the original matrix A is all 4 rows. And that means that, that a basis for the span of these 4 vectors is all 4 vectors. Okay, so that's 15. And so let's go to 4.8. 4.8. And so for 4.8, look at numbers 2 and 12. So 4.8, numbers 2 and 12. So let's look at number 2. So number 2, part A, says that A is equal to, the matrix A is equal to this matrix. 1, 0, negative 2, 1, 0. In the first row. This is the second row. Okay, so for part A, that's the matrix A. I want to find the rank and nullity of the matrix A by reducing it to row echelon form. Okay, so the goal is to find the rank of A and the nullity of A by reducing A to row echelon form. Okay, so let's get A to row echelon form. And so we use keep the first row the same in the beginning because there's a leading one already. I'm going to multiply the second, actually I'm going to switch the second and fourth rows. And so this row is going to go here, because it already has a leading one. And I'm going to make this one here. And I'm going to keep that row there. Okay. I'm going to then add 2 times this row to that row. So 2 times this row I'm going to add to that row. Good. And then I'm going to take that row the same. 0, 1, 3, 0, 4, negative 4. Okay, and then I'm going to take this row and add to that row. And I'm going to get 0, 0, 0, 1, negative 1. Okay, and now I'm going to take the second row and add to the third row. The second row is going to stay the same. Then I'm going to take the second row and add to the third row, and I'm going to get this. And if I take the negative of the third row and add to the fourth row, I get zeros here. And so I'm just going to go ahead and do that now. So now I have A in row echelon form, right? These are the leading ones of the first 3 rows, the zeros at the bottom, and every leading one in the lower consecutive row is furthest to the right than the leading one above it. So this is in row echelon form, and so I'm going to call that capital R. And so the rank of A, there are 3 leading ones, and so this implies that the rank of A is equal to 3. The rank, right, is the shared dimension, is the dimension of the row space and column space of A. They have the same dimension. And so if I take these 3 rows with leading ones here, all 3 of them, then these 3 rows is a basis for the row space of A. But the row space of R, the first three rows here is a basis for the row space of R. The row space of a matrix does not change under elementary row operations. So the row space of R is the same as the row space of A. And so these three rows are not just a basis for the row space of R, they're also a basis for the row space of A. And so we have that three vectors form a basis for the row space of A. And that means that the dimension of the row space of A is 3, and that means its rank is 3. By the nullity of A, we have by the dimension theorem that the rank of A plus the nullity of A is equal to n, which is the number of columns, and there are 5 columns here. And so if the rank of A is 3 plus the nullity of A is equal to 5, and that implies that the nullity of A is equal to 2. Okay? So the nullity of A is equal to 2, because we found its rank is 3, there's 3 leading ones, and here, and then by the dimension theorem, you could then get that the nullity is 2. Okay, so that's by the dimension theorem I discussed in the lecture. Okay, so now we found both the rank, this is done, and the nullity by reducing it to row echelon form, also done. Okay, so that's, and 2b is similar. So let's go to 4.9. So now for 4.9, so for 4.9, it's numbers 9 and 26. So let's do number 9. Okay? So for number 9, it says that use matrix multiplication to find the image of the vector 3, negative 4. When it is rotated through the origin through certain angles. So you have the vector negative 3, 3 comma negative 4. Okay, I'm going to take that vector 3 comma negative 4, and I'm going to rotate about the origin through the following angles. Okay, so I'm going to take that vector 3, negative 4 point. I'm going to rotate that that vector about the origin through the following angles. And so part A is a rotation of theta equals 30 degrees. Okay, as this rotation is counterclockwise, so keep in mind that this is always a positive angle rotation about the origin is a counterclockwise rotation. That's the assumption, okay? The positive angle, we're going counterclockwise. Okay, so a picture of that would be if you take the vector 3 comma negative 4, it would look like this. And we're going to rotate that counterclockwise 30 degrees. And so we're just going to take that, and so we're just going to rotate this angle by 30 degrees counterclockwise. Okay? And so to do that, you just love, so the standard matrix for this operation is the first column is cosine theta, sine theta, and the second column is negative sine theta, cosine theta. Okay? And so you just plug in the angle into that matrix, and you left multiply your column matrix for that. So for instance, here you have 3, negative 4, and you just left multiply it by that matrix, where theta is 30 degrees. So that would be cosine 30 degrees, sine 30 degrees. And the second column would be negative sine 30 degrees, cosine 30 degrees. Okay? And so we're just going to take 3, negative 4, left multiplied by that, and that will tell us the image. That will tell us the result of taking that vector 3 comma negative 4 and rotating it counterclockwise 30 degrees about the origin. Okay? And so what you get is that this is equal to, if you calculate cosine 30 degrees, you get root 3 over 2. Okay, so root 3 over 2 is cosine 30 degrees. Sine of 30 degrees is 1/2, and so negative 1/2 here, positive 1/2 there, and 3, negative 4 is your input vector. And so you multiply those two matrices, and so root 3 over 2 times 3 plus negative 1/2 times negative 4. And so that's going to be 3 root 3 over 2 plus 2. So that's 3 root 3 plus 4 over 2. Okay, when you combine them. Good. And then here you get 3/2 plus, you get 3/2 minus 2 root 3. Or it's 3 minus 4 root 3 all over 2. Okay, and so that's your resulting vector when you rotate that through the angle 30 degrees, about counterclockwise of the origin. That's assumed. Counterclockwise is not always said, it's just assumed. If you have a negative angle, that would mean that a negative angle counterclockwise would mean if you took the positive value of it, you'd be going clockwise, right? So if you're rotating counterclockwise, you're going this way, right? But if you're going a positive angle like that, you'd be going that way. If you're going a negative angle, let's say you'd be going that way, right? So a negative angle would make you go clockwise, a positive angle would make you go counterclockwise. Okay, and so that's it. And so for B, C, and D, you just use a different angle when you plug it into this matrix, and you left multiply your starting vector by T for a different angle here for these four. And you left multiplied by the corresponding matrix determined by your other angle of theta, and you get your output. Okay? And so that shows you how to do the rest of the parts for number 9 there. Okay. So now that's 4.9. So 4.10 is 7 and 9. Okay, so for number 7, let's look at part A. So part A says a rotation of 90 degrees followed by a reflection about the line y equals x. So let's look at that. So we're going to rotate 90 degrees. Then we're going to reflect about the line y equals x. Okay? And the goal is to find the standard matrix. For the composition in R2. Okay, so we're dealing with vectors with 2 components. We're dealing with vectors living in R2. And so we want to find the standard matrix for the operation of first rotating 90 degrees and then reflecting about the line y equals x. So if you rotate 90 degrees, then that's going to be a rotation of 90, so that's going to be this matrix, cosine theta, sine theta, first column, negative sine theta, cosine theta. And it's just going to be this matrix when theta is 90 degrees. Okay? And so that's the operator of rotating 90 degrees. Left multiplication by that matrix where theta is 90 degrees. And then reflecting about the line y equals x is just the matrix, the standard matrix for that would be that. The first column is 0, 1, and the second column is 1, 0. Okay? And so then, so first, okay, so what is this matrix? Well, when you plug in 90 degrees, cosine of 90 degrees is 0. And sine of 90 degrees is 1. And so you get that matrix. Okay, so first you left multiplied by this matrix, and then you left multiplied by that matrix. And so the standard matrix is first left multiplication by this matrix, then left multiplying by that matrix. And so it matters the order in which you put these matrices, right? So first left multiplication by this, and then left multiplication by that. And if you multiply those two matrices in that order, you will get 1, 0, 0, negative 1. And so this is the answer. That is the standard matrix for first rotation by 90 degrees about the origin counterclockwise, and then reflecting about the line y equals x. You find the standard matrix for each operation, and then in the correct order, you multiply those matrices to find the standard matrix for the composition of the two functions. Okay? Because remember, there's a theorem that says the identity matrix for T sub A composed with T sub B is the identity matrix for T sub A times the the standard matrix for T sub A composed of T sub B is equal to the standard matrix of T sub A times the standard matrix of T sub B. And so what we're doing here is we're composing these two functions, and the rotating of 90 degrees would be like actually T sub B, ironically, and this would be T sub A. And so what we want is the standard matrix for T sub A composed with T sub B. T sub B is first, and then T sub A. And so then that would be this order. And that's exactly what we did. This was T sub A. This is the identity matrix for that operator. And this is this is T sub B, sorry. This is T sub B, and then that's the identity operator for T sub A. And so we're just multiplying in that order to get that. Okay. Remember, the order of the composition is read from right to left. So when I say T sub A composed of T sub B, it means T sub A first, and then T sub A. So that's T sub B first, then T sub A. Okay, so it's all that. So that's number 7 for 4.10. Okay, so I went through problems in all of 15 sections that are on this test, okay? And so go over the homework, go over all the lectures, and be ready for the test. Okay, have a good day. Bye.